So in the previous lecture, we obtained the equation for the field at 2 omega, the spatial dependence. So you have this first order derivative in z, which is related to so this is the amplitude of the field at 2 omega, which is related to the square of the original field at omega, right? So if you quickly recall, we got this equation by undertaking something called the slowly varying envelope approximation. E2 omega as well as E omega, these fields do not vary too much across a length scale of lambda along the direction of propagation. So as these fields are more or less constant across the length scale, the higher order derivatives are neglected in comparison to the lower order derivatives. That's something that we already done in the previous lecture. So now what I want to do is basically take this equation number 13, as I said, and I want to solve this equation as a function of z. So one is that we explicitly write down also the equation governing the field at omega and its z dependence. That we are not doing here. So we make another approximation which involves assuming that this particular field at omega is non-depleting pump. What that means is that the field strength remains same across my nonlinear medium. E at omega at z is same as what it was at the starting of the material, which is at z equal to 0. So it remains constant. So if I take this nonlinear term to be constant, I can quickly integrate. So only term in the integration, it is basically the exponential I delta kz dz. So that is the only term that needs to be integrated from 0 to let's say z. So what we get is this very characteristic solution that my E2 omega is related to a sinc function, right? And you know the properties of the sinc. So I am plotting this sinc function as a function of the arguments. Let us say I am plotting this z, right? So and if delta k is finite, non-zero, and then you will see that at z equal to 0, you get the maximum value, and you get this sinc square dependence for the intensity of the 2 omega field, second harmonically generated field. And you see now the closer delta k is to 0, right, greater is going to be the generation of the intensity of the I2 omega field, right? And one can associate a sort of a length scale or a coherence length within which there is a significant generation of the second harmonic field. So what really needs to be done is that one needs to make sure that delta k is actually as small as possible, and in the best case scenario it should be equal to 0. So that particular aspect is what is called as phase matching. So I'll come to that in a moment. But we have already made this approximation that the pump or the input field at omega is non-depleting. But in reality, what would happen, for example, in a thick crystal, you have this pump light coming in, and then you see that the amplitude of the pump slowly decreases across the nonlinear crystal as the second harmonic field gets enhanced. So on propagation, the 2 photons from the original pump converted into a single photon at 2 omega. So this is the wave mixing process. You have 2 photons at omega combining together to form a single photon at 2 omega. This is what I meant by saying that photons in general in the linear regime cannot talk to each other. But here you see you have 2 photons actually combining in presence of the nonlinear medium to produce a photon at twice the frequency, which is the second harmonically generated photon. So in general, these are wave mixing processes where one could have in principle 2 fields, one at omega 1, another at omega 2, generating a third field at omega 3, such a way that this condition is satisfied. And simultaneously, it must also satisfy the condition that the k vectors also add up to produce this k1 plus k2 adds up to produce k3. The generated k minus the input k is what is the difference we call delta k. If you go back and look, so this is precisely what was our delta k. In this situation, we are looking at a collinear propagation. So you have propagation constant of the omega field minus the propagation constant at the 2 omega field. It's this difference which is what is delta k, and setting delta k to 0 produces the maximum amount of the second harmonically generated field. So before I go ahead, I just want to give you this general setting of the second order nonlinearity. So these are processes that are dependent on the second order coefficient chi2. Remember, in our polarization, this was the term that was multiplying all the products. So basically, such a second order process involves, in general, involves three fields. These are such that combinations of two produces a third one. For example, the combination that we looked at is when omega 1 is equal to omega 2 is equal to omega, what we would call as degenerate wave mixing, and it produces a 2 omega field, which is the second harmonically generated field, which is simply the addition of omega 1 plus omega 2. Remember, at the same time, we also looked at rectification, which is this fourth process listed here, where again omega 1 and omega 2 are the same. These are degenerate, but what we are looking at is a difference frequency generation, such a way that it produces a field at DC, which is what we call as rectification. In general, we could also produce, if there are two arbitrary frequencies, omega 1 and omega 2, we could produce omega 3, which is a sum frequency generation, or the difference frequency generation, and so on. All right, so in the situation of the second harmonic generation, microscopically, one can think of it as two photons of omega being absorbed to produce a single photon at 2 omega. And of course, one needs to match or conserve energy. That would mean that that omega 1 plus omega 2 should be omega 3, right? This is obtained through energy conservation, where one is looking at now the difference between the generated field and the input fields. Absolutely similarly or simultaneously, the momenta of these photons also needs to be matched. So here we are looking at, for example, we are looking at co-propagation of the fields. So you have K1 arising from the photon number 1, K2 arising from the photon number 2, these two producing K3, which is basically 2K. So again, we are looking at the difference between the inputs and the output, and that is delta K. So for energy conservation, we require that delta E is 0. For linear momentum conservation, we require that delta K is 0. And both of these needs to happen for such a nonlinear parametric process to occur. Now one would wonder, is the angular momentum conserved? Yes, indeed it is conserved. And basically the angular momentum governs the internal transition inside the nonlinear medium. So these are related to the electronic transitions, and the change in the angular momentum of the electronic state is basically should be matched with the incoming angular momentum. So for example, for dipole transitions, if you look at the total angular momentum of the electron, it arises from the orbital angular momentum, the spin angular momentum, and something which is coming from the nucleus. So that the total angular momentum is F, and if the change in F between when I'm going from the initial state to the final state, if the change is plus minus 1, these are allowed dipole allowed transitions, and these involve either absorption or emission of appropriately right or left circularly polarized light. So in the sense that the angular momentum contained in the photon is given to the medium, okay, so that the electron changes its overall angular momentum, or as the electron comes down, it gives away this 1 unit of change in the angular momentum to the light field. Hence, we get a circularly polarized light out. So what we are going to look at is basically this business of phase matching, which is the matching of the linear momentum. But now let's focus our attention on the collinear phase matching. That is, my K1 and K2 are also co-propagating with respect to K3. Now, if you quickly recall in my previous lecture, I had already told you that this matching, it basically boils down to matching of the refractive indices at 2 omega and at omega. And we will see how that is done. I'll give you one example of collinear phase matching, and that will probably shed more clarity on this idea. So of course, in general, the phase matching need not be collinear, where what one does is basically aligns the two fields in such a way that vectorially k1 plus k2 happens to be k3. In such a situation, one would be able to undertake the phase matching and hence generate this new field k3 in that direction, so as to provide maximum conversion, maximum wave mixing probability for k1 and k2 to produce k3. So you see, in general, the way to go about solving these self-consistently, because now you have got three different fields. There are Maxwell's wave equations which are governing fields at these three different frequencies. One is at omega 1, one is at omega 2, one is at omega 3, and these equations are coupled. Again, one can take the slowly varying envelope approximation and so on and so forth. So what one gets is basically coupled set of nonlinear partial differential equations, and it is this coupled set that needs to be solved self-consistently. And this is what I was talking about very early on when we talked about the Born approximation. I said there is a way to do the coupled wave analysis, which is to now solve the equations governing the three fields simultaneously and self-consistently, and that is usually undertaken numerically. I will not get into that, but you understand what the philosophy behind it is, where one looks at basically the various conversions across the length of the linear medium, the various transformations of frequencies and fields from one to another. All right, so now let us get back to this collinear phase matching. So as I said, we have ensured that the energy is conserved, that is 2 omega minus 2 times omega is 0, right? And now we are ensuring that even the momentum is conserved for this particular nonlinear process to happen. What it boils down to is there is always going to be a difference between the refractive indices at 2 omega and omega. So how does one actually ensure that these two refractive indices are same, given that intrinsically all real media, linear or nonlinear, are actually intrinsically dispersive? So how does one do it? I'm going to quickly indicate to you how this is done. So for this, I'm now briefly introducing to you a birefringent crystal. So a birefringent material in this scenario is a crystal where we have two different refractive indices experienced by two different polarizations. There is something called an E ray and an O ray. E stands for the extraordinary ray and O stands for the ordinary ray. So what it tells you is that the ordinary ray is such that that particular polarization experiences in any direction you propagate through the crystal, it would experience the same refractive index. Whereas the extraordinary ray is such that depending on the direction of propagation within the crystal, it will experience different values of the refractive index. And of course, in the crystal, there is something called the optic axis. So optic axis is a direction, a special direction. For example, this is a uniaxial crystal in the sense that there is one axis along which the propagation of the two polarizations is such that the refractive indices are the same. All right. So in general, a medium could be biaxial, but we will not get into that detail. So imagine that the optic axis is along the vertical direction as indicated in this. And what I'm plotting is that as I change my angle with respect to the optic axis, this theta indicates that angle, you will see that if I draw a circle, okay, this is what is called as index surface. Of course, there are three dimensions. What I have is a spherical surface which indicates uniform refractive index of a polarization along all directions within the crystal. In contrast, for the extraordinary ray, for the extraordinary light, for the other polarization, what one has is an ellipsoidal surface. So in the plane it is an ellipse. What it tells you is that along the theta equal to 0 direction, which is my optic axis direction, the refractive index match, whereas as you go away from the optic axis in terms of theta, so you see that if you, for example, if you go through at theta equal to pi by 2, you see that these 2 points indicate that the refractive indices are actually different. One is the ordinary ray refractive index, and other one is the extraordinary ray refractive index. The fact that the extraordinary ray has a value which is larger than the ordinary ray's refractive index in any arbitrary direction, this happens to be classified as a positive uniaxial crystal. But basically, this dependence on theta, which is the angle with respect to the optic axis, can be captured in the following manner. That is, my refractive index, extraordinary refractive index with respect to theta, is cosine square theta by NO square plus sine square theta by NE square. Remember, this value of NE is simply the maximum value it takes at theta equal to pi by 2. So as I change now my theta, I would basically get this index surface. It is a nice pictorial representation of trying to figure out what is the direction along which what would be the different values that the refractive index will take for two different polarizations, right, for the extraordinary and the ordinary ray. This is how at a particular frequency, depending on the polarization and the direction of propagation, I would be having two different values for the refractive indices. Now let's look at dispersion. So material dispersion is such that I am looking at this crystal which is transparent. That would mean that we are away from the anomalous region. That is, my dn over d omega is going to be positive, right? This we have already studied earlier, which talks about normal dispersion. So what you get is that as I increase my frequency from omega to 2 omega, the extraordinary ray refractive index varies linearly and it increases. Similarly, the ordinary ray also varies. So now you see, what I am interested is in the fact that regime where the omega refractive index for omega for the extraordinary ray matches with the refractive index for the ordinary ray at 2 omega, right? So let us make this index surface. So I'm coming back to this figure on the right hand side of your screen at the bottom. So if I'm now looking at this particular picture, so what we have done is we have plotted this index surface at two different frequencies. One is at omega and the other one is at 2 omega. The solid black lines indicate the index surfaces for the field at omega. So this is precisely what we had plotted earlier. But you see that at 2 omega, the refractive index actually increases for both the ordinary and the extraordinary ray. So the ordinary ray maps on to a larger circle, which is the dashed line shown here, right? This is the dashed line. And similarly, the extraordinary ray gets mapped on to the larger ellipse at 2 omega, right? So this is what is these are now the two different index surfaces plotted for both the ordinary and the extraordinary ray at omega and 2 omega. And you can clearly see that there are these points where the ordinary ray at 2 omega actually matches with the extraordinary ray at omega. So you see, this point of intersection is precisely the direction in which, if I propagate such a way that if my polarization of my pump beam is such that it corresponds to the extraordinary ray at omega in this nonlinear uniaxial birefringent crystal, if I come in at an angle from the optic axis such a way that my omega field has a polarization which is along the extraordinary ray direction, in that situation, I'll generate second harmonic field having a polarization corresponding to the ordinary ray associated with that crystal. So that is how you see along a particular direction. So now I have got collinear propagation along a special direction inside a crystal, which will actually make sure that the difference between the two is zero, simply because we have used the birefringence, wherein there are two different polarizations now, which play around together in such a way that we need to put in the pump or the input field with a particular polarization so as to generate the second harmonic field at a different polarization. And indeed, this is going to happen only along this direction, which is the direction along which the two index surfaces, one corresponding to the extraordinary ray, intersects with the index surface corresponding to the ordinary ray at 2 omega. Alright, so this is how one does phase matching, and with this I have basically conveyed to you the essential features of nonlinear generation, taking the example of only the second harmonic generation, and you can clearly see it is the intensity dependence of the input field that needs to be high or strong enough for us to access the nonlinearity of the medium and hence generate this field at a higher frequency. And this has been possible only after the advent of the lasers, where one could pack in large amplitudes or basically immense power into extremely small volumes so as to produce large intensity or large electric fields, so that one actually gets significant amount of nonlinear generation. All right, thank you very much.